Okay, hi everyone. So today we'll continue with the week 9 discussion which we had last session. Okay, so we start somewhere where we were using combinational circuit to get a counter design, and we saw that we could add a delay and we'll be the one to set frequencies, and when these all are done properly, then we'll be able to get output. But getting and adding delays and getting the outputs in different time would not be very efficient. So for this kind of problems, right, we will have something called sequential uh, circuits now. So in sequential circuits, so to achieve this kind of counter sort of problem where you have to make sure that you remember your previous state or using your previous state to get your next state sort of thing. So for this, what we will do is we will use something called programmable delay element. We will use programmable delay element, and that is nothing but a flip flop. We call it a flip flop. And for the flip flop, the how we denote it is there is a box with a small mark here. So basically, this is for clock, which gives the input like clock signals. We tell it clock signals, CLOCK, clock signals, and we mostly denote it using CLK. Okay, so we use this clock signals, and based on this clock signals, we'll have to understand that whenever there is a certain input going in, certain output comes out depending on the clock signal. Okay, so first one we'll start with a basic flip flop, that is a D flip flop. So it is a D flip flop. So for D flip flop, how you'll denote it is, so you have a box, and then let's say we have a clock here. Here the input will be D and the output will be called as Q. So this is how we'll be denoting a D flip flop. The input will be D and the output will give you Q. And basically what it does is when D is equal to 0, right? So when D is 0, okay, let's come to this later when we are trying to figure out the table for this particular flip flop. So now what you have to understand is, so clock has two edges. One will be rising edge and the other one will be falling edge. What is rising edge and falling edges? Let's say you have signal like this. This is how clock will be sent. When you have something like this goes down, up sort of. Okay. So this is clock. So this up which is going, this will be the rising edge, and the other side where it goes down is the falling edge. So this will be the rising edge. And it is also called positive edge. And which goes down, this is called as falling edge or negative edge. Negative edge, okay? So now what we'll do is, so if you see we are giving inputs here, right? We're giving input here. So we'll try to tell that this entire flip-flop is based on this particular clock. How? So we will make sure that whenever the input goes high, let's say the first one we are talking about a positive edge. So when we are talking about a positive edge, let's say it is positively triggered. Whenever a positive edge goes high, the output should change. If that is the condition, then what we will do, whenever the clock signal is going high, that is whenever it is going high here, here and here, only at that time you can see that the output comes out. And all other times the output will remain the same without any change. It will not change. The output will change, that is will come here only during the positive edge. During the negative edge, nothing happens. So that is what we are talking about, positive edge. And the same thing for negative edge, what happens is whenever it comes here, here and here, only then the output will be triggered. Till then there will be no difference in the output. Only when the clock edge becomes negative, only then the output will be triggered. Okay, so that is for the clock bits. So now let's say, this particular flip flop, right? It is nothing bigger, and there's nothing bigger like what kind of output will come. The only thing that will happen is whatever input you're giving, that particular output should come. So basically your q will be equal to d. That is what we are trying to tell. But now, with respect to this clock, we will plot the graph and see how it works for the deep flip flop. So now let's say we have a clock signal. So let's say this is our clock signal. So now this is a clock signal. So this is positive edge, positive edge, positive edge. This is our clock. Next, I have my D. So let's say I'm giving my D something as, let's say it is here, it is over here, and then from here it moves on to the next one, 2 here, and then to, let's say, 3, state 3, and then to state 4. Let's say it's like this. So this will be 1, 2, 3, and 4. Let's say this is what we are giving for D. This is the input which is being given. Now what we have to find is we have to find the Q. We have to find a Q. So if you see, and let's take this is positive edge. So if it is positive edge, only during positive here, positive trigger, it should change. So this is a positive edge and this is another positive edge. And this is another. Only during at this point, the output should change. So initially what happens is, initially it will be, we will not consider this will be don't care, because initially we do not know what's happening in D. So initially it will be a don't care condition because it happens before the clock, right? So before the clock we don't know. Once the clock signal begins, that is when we will get our output. Our output here will be whatever the D is there, that will be our output. So now if you see for your positive side, right, this is your positive side. So when your positive is triggered, you can see your D is 2, right? So, and this is your negative one. This is for the negative. So if you see the positive here, what are you getting? You get something. For right now, let's forget about all the delay that's there. We'll just focus on D giving Q. So what will happen is at this entire, not the entire thing. So at this edge, if you see what happens at this edge, it is basically 2, right? It's basically state 2. So it will start with state 2. Okay. And you see that we always call flip flop as edge triggered. It is edge triggered. Okay. It is called edge triggered. Okay. So now what we will do is, what so at this edge, if you see at this edge we had our D input as 2. So what happens, your output will be 2, and then what happens is your output will remain 2 till the next clock cycle. And why nothing will change is because till there is another positive edge trigger, there will be nothing to change. That's how the entire edge trigger works. Okay, so now at this positive, you see that the output here is 4. So what happens? Okay, there will be a small delay like this that will happen. We will come back to this particular delay later. But for now, you understand that once edge is triggered, whatever the input is, that you will get that input, and it will continue till the next particular positive edge trigger. Okay, so that is how the positive edge trigger works. And the same thing if you're talking about negative trigger, right? If we say this is a negative edge trigger, instead of the positive, will see the negative side. So if you see the negative side here, right? So what happens till here, till this particular point, it will be considered as don't care, because till then we wouldn't know what is happening because we do not have clock cycle of negative triggered before that. So after this negative trigger, whatever is present in D, that will come in D. At that point 3 is present, and that will remain till the next neg- negative trigger. Okay, so that is how your positive trigger and negative trigger will work. And now what we will do is we'll be the one who will be controlling this clock signals. Like how much of let's say what should be the frequency. If I give 1 megahertz of clock frequency, okay, what happens is you will get a time of 1 microsecond. So that will be the time difference that you will get. So you basically have to calculate it and give the frequency of the clock accordingly, and according to the clock signal you will be able to control your output that you're getting. Okay, so that is one thing. So the continuation of that, right? So now if you look at the counter which we were seeing with the combinational part, with the combinational part, if you remember, we had a full adder. Let's say we have a full adder. So full adder, we had A naught, then we have A1, I mean 1, and we got S naught, and we were trying to give this back here, right? We were trying to give this next state to the current state here. So for that, we will add a flip flop here, which has like clock, and here this will be considered as the input, and the output here will go as the input for this particular adder. This will be Q. So this way, this clock, it will control the frequency. So you will give the frequency, it will control the time, and depending on that, not every output goes here, only the output which you prefer depending on the frequency you have given, only that goes here. And that's how you will control your counter here. Okay, so let's say we are trying to plot this particular graph. Let's say we want to plot this graph, and I have a clock signal here. I have a clock signal here, right? Like this, let's say. So 1 and 2. Okay, so I have a clock signal here. So how does it work? And let's say you have, this is S naught, right? So this will go from let's say you have all the 4 bits, so it's a 4-bit adder, same thing. So you will have another full adder FA1, which will have A1, which, and it will get added to 0 because we're adding 1. And then here we go and give S1, and here again the delay same, the flip flop is here and to go here. So here the output, what happens is once when the clock starts, there is already an output present. So we will not care that. And once, so basically not care as in initially it is 0. So we don't care that. And the next what happens is after this clock there is a slight delay, and after that delay the counter will change to the next state. The next state will be 0001. Until where will it last? Will it last till let's say this line is 1, this line is 2, this line is 3. So till where will this state last? 1, 2, or 3?
will last till 2.
Yes, it will last till 2. And why? Because if you see here we are taking positive edge. For positive edge, the output will change only at the positive edge whenever positive edge is triggered. So it will last till here, and after this, again, there is a very slight delay. After that, it will move to the next state, which is 0010, and that will last till the next positive edge. Okay, so this is how the entire counter goes on. Okay. So this will be your graph for your counter for D flip flop. Okay. So next, to okay, before we move on to D latch, which is like a component to construct the flop, let me know if you have any doubts still here, like overview of how the flip flop works and how D flip flop works exactly. If there are no doubts, then we can continue with latch. Okay. So next is D latch. So what is D latch is to construct the flip flop itself. So if you see now this is a flip flop. For flip flop, what do you have? You have a clock signal, you have input D, output Q. Okay, and let's say we call it flip flop. So here on let's say rising edge, right? Data will go through and remaining in the other state, it will just remain in the same state till it goes to the next rising edge. So that is how we talked about this, and we call this is edge triggered because only at the edge it is changing. Now to construct this, we bring something called a latch, and for latch we denote it by a box like this, and then we have clock, we have D, and output Q. If you see the difference of denoting this will be this particular shape here. Latch will not have it. Okay, and what is latch? Latch is level triggered. Latch is level triggered. Level triggered as in you have seen a clock, right? Clock signal. Now clock, this is the clock signal. So now in this clock signal, whenever something on this edge happen, it's tailed till the next edge. So we call it edge. Now here for the latch, this space, and this entire space. This is what we call level, and anything that changes in this particular duration, edge trigger was only at that point. Level is at this entire duration. Okay, this will be level triggered, and this up it is positive level triggered, and down is negative level triggered. Okay, that's it. That's the difference between. Now, if you see the main difference between latch and flip flop, latch level triggered and flip flop will be edge triggered. Okay. So now moving on to this latch in detail. So let's say we have a clock signal. Let's draw a clock signal now. Okay. So this is clock signal, and let's say these are positive sides. And let me tell. Let's have positive. Okay. Let's have it. Positive level triggered. It is positive level triggered, and this is clock. And my d, let me give you input something like let's say I have 1 here. This is state 1, then I have state 2, state 3, then state 4, 5, and then let's say I have 6. So I have 1, 2, 3, 4, 5, and 6 states. This is the input that I have given. Now we have to find the output. So as we told, this is for latch and it is level triggered and positive level triggered. So in positive level triggered, so it starts here, right? Positive edge starts here. So let me. So this is 1, and this is the next positive. This is the next positive. And for negative, this is the negative where it starts. This is also negative where it starts. So now here, initially it will be in a don't care condition. And after that, what happens is once it is positive triggered here, whatever the input is there, that will be given in the output. So if you see in the input here, you have 2 here, then you have 3 here, you also have 4 half here, right? So this will be the positive side of the level trigger. Next it goes to the negative side. In negative side, what happens is this is not cared. What happens, whatever already existed, that will continue. So this 4 state will continue till the next positive level. Once the positive level reaches, whatever the output you have, input you have here, that will come in the output here. Okay, so you will get that particular output here, 6. So this is how your entire latch works. If you take the same example, right, if it was a flip flop at this point, at this point here, it will be changing to 2. And after changing to 2, what will happen is till the next particular positive edge, it will be 2, and after that it will change to 6. But here we consider the entire level, so it changes to 2, 3, 4, and finally when the new, again the same thing, again for this edge, whatever the output input is given here, that will come as a output here. Okay, so this is how you differentiate latch, flip flop. Okay, latch is level triggered, flip flop is edge triggered. So the same thing if we are talking about negative edge. If we are talking about negative level trigger, what happens here is, so initially this is a negative edge. So what is the negative edge value here? It is 1. So you will have 1, then 2 will start here. After that, this is positive. So till the next negative, it will remain 2. Then at this point it is 4. So again here it will start with 4, then it will be 5, and then till the positive, okay, it is also 6 here. The 6 is starting before the positive it starts, and this 6 will continue till the next negative trigger. Okay, so this is how your latch performs. So if you see here from this entire image, when clock is equal to 1, right? So what happens, your q, this will be for positive, we're talking about positive. When clock is 1, you will have q whatever is given in d, and when clock is 0, your next state will be same as the previous state. Your qn plus 1 will be equal to qn. So it is nothing but your, if your clock is equal to 1, then you have q is equal to d, else you have q is equal to q. So basically this is the important part. And this one, if you see, it is just a multiplexer, right? You just choose if or if else. So this can be easily denoted using multiplexer. How? First, you have a multiplexer like this. You have 0, 1. Then you have D and a clock is given. So what is basically it's telling when your clock is 1. Okay, so in the multiplexer, when the clock is 0, which is chosen, there are two select lines, one output line. So when your clock is 0, this line, the first line is chosen, right? So in the first line, what do you want? If your clock is 0, you want your qn plus 1 to be equal to qn. So your q is the output. So your qn plus 1 will basically be the qn. So this will be your first thing. And for the when clock is equal to 1, your q will be equal to d. So basically your d q. That's it. Okay. It will go directly like that. This one is like this. Okay. So this is your multiplexer diagram for this particular latch. Which latch? D latch. This is for the D latch. Okay. So now the same diagram can be also written in a form where inverters are added. And why those are added? Because to increase the delay sort of thing, which will be learned in more like in a transistor level detailedly, which is not a scope of this particular course here, but you can just understand that here you will use buffers. How? So you will use a knot here, then you will use knot here, and this knot is the one which will go here. So this will be here like this. Okay, so basically like this. This is your Q and this is your D. Now if you see, right, uh, if you see here, so there is one knot here and another knot here. So the knot and knot, even number of knot, it is again positive. The D is equal to Q. That's how it will be. And if you see this loop, again you can see there is a knot here and another knot here. And again these two knots get cancelled and again it's the same. Q is equal to Q. Okay. Okay. And if you remember, we also have something called race condition. So what is race condition is? So do any of you remember race condition? Okay, so if you see the race condition itself is something like here if you see one value here is getting again overwritten by the other one, right? So race condition is something where if one value is being like accessed by another one and if it gets corrupted, that is you didn't want to change it but the other value changed it, then that is what we call race condition. But here the race condition will not happen. Why? It is because it will be the same value. It will be the same value, right? Because that is what we are trying to do. We are just trying to give the q same back in. So there is nothing called race condition here. I mean, the race condition here will be no. There will be no race condition in this particular scenario. Okay. So this is the positive latch. Okay, so there is a clock also here. Okay, so this is the positive latch. Now let's go to the negative latch. How will you give a negative latch? So again, you have a multiplexer. You have a D input. You have Q output. Then this Q will be given back for another like next state. There are two ways you can do the negative one. First one, you can just have it 0, 1 and give clock bar. So this way it will toggle the zeros and ones. So when it toggles zeros and ones, what happens? So when your clock is 0, when your clock is 0, which one will work, it will go to this, because clock bar will become 1 and it will start operating this. You can either do it this way, or the other way is you give clock, and up you give 1 and 0. You interchange this. This is also same. So whenever it is 0, what will happen? Whenever it is 0, it will start with D.
Will pass the data.
Correct. Okay. So you can do it in most of the ways. Most of the time, we usually follow something like this one only. You will use clock bar, easier. So you'll use clock bar. So this will be for not positive. This will be negative latch. The above one was positive latch. This was positive latch. And this is negative latch. Okay. So these are like basic things about how latch. The D latch is the simplest of all. So that this is how latch flip flop. You will get the outputs, and inputs are given, and how you'll get the outputs. Okay. Okay. So if you're able to understand this, then we can move on to a higher concept like master slave flip flop.
Yes, ma'am.
Okay. Okay. So the next one will be master slave flip flop. A master slave D flip flop. We will see for D flip flop. So here, if you see, what happens is two back to back. There are two back to back latches, and what we will see is how these latches are arranged so that we will get the desired output. Okay. So how the latches are given is, first there is a master, and then there is next one which is slave. What happens is, master is the one which we will which master latch is the one which will drive the slave latch, and you will get the final output. So now let's talk about positive edge triggered flip flop. Positive edge triggered flip flop. So for positive edge trigger flip flop, your master latch will be negative latch. Okay. We will see why we have negative, and your slave will be positive latch. Let's see why it is positive and negative once we go to the what do you call the diagram, the circuit, the graph. Okay. So now the circuit for this side. So this is a negative latch. So how your negative latches? You have a multiplexer, 0, 1, and then you have a clock bar. You have input D. Then you have Q. We call this QM, which is in the mediator, like in between. So this is the Q from the master. Okay. And this Q will be again given here as well. Okay. And then we have another positive latch. We have another positive latch here. So this will be 0, 1, and you will have clock as usual. And again, there is an input. Here again, there is another Q which goes all the way to here. This will be the final Q. Okay. And this D, in this D, where you will get this, you will get it from this master. This is what will drive your slave. Okay. So, and if you see, this is negative latch clock bar, and this is positive latch clock. So this entire master will work on negative level, and this entire slave will work on positive level. So this half is master and the next half is slave. This is how the circuit is for your master slave D flip flop, and this is basically for positive edge triggered. Now we will plot it out and see why is it like negative master and positive sleep. So now here I will, so this is your clock signal. Okay, so this is your clock signal. And then let's say the D which we have is something like this. And okay, so now let's say this is the D that we have, that is here at this point. This is the input that is given. Now the expected Q will be, so let's say we are drawing for, this is the positive edge, positive edge, positive edge. Now, okay. So now this is the expected Q. So what happens till positive edge? Nothing, don't care, right? So you have a don't care condition there. And after the don't care condition, what happens? You will get whatever you get for D. Your D is here. So you got your don't care. After that, you got your D. Here, D. And what happens? It is a flip flop, right? So what is the how does flip flop work? Till where do I extend it?
It will extend till the next rise.
Yeah, it will go to the next tries. And now in the next tries, whatever you get here, after some delay, it will go and do whatever happens in that particular edge, right? Okay. So now this is a expected result. For D flip flop, this is a expected result. Now from our master slave, we'll try to find out what we will be getting. Now we will first plot QM. QM is a negative latch. Okay. So now for QM, you have D and you have clock bar. Now for this is a negative latch. Now what happens? The first is a negative thing. So first is a negative thing, right? So in the negative thing, how will you start it? What will be the initial one? The negative edge. So this is basically a negative level. And this is also a negative latch. Then how to begin? Where will it be 0 or 1? It will be 1, right? Because we have D, we have clock. So basically our QM will replicate D when negative latch, when will it replicate? In the negative level. So initially it is negative level. So our QM will replicate D, right? So we will be getting whatever D is having. So basically we will have this. Okay. So now positive one starts. So what happens in the positive side now?
It will hold it, like it will
Continue. Yes, correct.
continue the previous state.
And it will come till here, till the point where there is negative level again. Now in the negative level, what will happen?
It will pass the data.
Yeah, D, right? You will get whatever is in D. So D here is above here. So after some delay, it will go up here, and then your entire this particular negative one will be given here till here. And now after this, what happens again? Is it positive? Will positive thing affect the negative latch? No, right? So again it will continue whatever was there till the next negative level. So this will be your QM. Okay. Now plotting for Q, if you see Q, this is a positive latch. So for positive latch, your D is basically the QM. That is, the QM is the input for this particular latch, and your output is Q. So now my Q, output is Q. Okay. So after the output is Q, what will you do? Your input is QM. Your input is QM, and your clock here, positive side. Positive, no? So this is positive latch. So initially, what happens? What will we do initially? It is on the negative level. So what happens initially?
It will be don't care.
Correct. It will be don't care. After that, in the positive side, we will be following which one? Will be following the D or QM.
QM.
Correct. We'll be following QM. So after some delay, it will come to QM, which is here 0. So it will come to 0 till where this is the positive side, right? So, and for the entire positive side, your QM, what is happening? So this is your entire positive side here. So this is the entire positive side, and your QM is remaining in 0. So it will remain 0 here. And in the negative cycle, there are so many changes happening in QM. Now, what will be our output here?
It will hold the previous one.
It will remain same because it is in the negative side and ours is positive latch. So it will remain same. And then what happens? Again, you're coming to the positive side here. You're coming to the positive side here. So in the positive side here, now what happens? Your QM is above. It is 1. So after some delay, it will also change to 1 and continue. Okay. So now is your Q expected same as Q? It is same, right? You got the same output here. Okay. So this way you'll be able to construct a master slave D flip flop which is positively triggered. And if you want a, okay, so now what did we do? For positive trigger, our master was negative latch, slave was positive latch. Now if I want a negative edge triggered flip flop, negative edge triggered flip flop, then what will be the master?
The master should be a positive latch and the slave should be a negative latch.
Negative latch. Okay.
Yes.
So primarily you don't have to buy heart anything as such. You just have to know how the entire latch works, like the timing diagram especially. So if you see now in this timing diagram itself, there were few areas where we left as delays, right? So if you see, let's take at this point, okay? No, let's come to this one. Let's come to this point, okay? Or this point, or where is it evident? Okay, let's take here. Is it clear here? Going here and then up. I think okay, let's take this. Let's start from this point. So now in this queue, if you see, after this point, it is going here. QM becomes 1 at this point. Q, we are having a slight delay here, right? This slight delay, right? So this is one of the delays. Okay, I want you to keep this in mind. There is this one kind of delay, and there is another kind of delay where, let's say, you have something like here. Mm, or okay, first let me explain what are the delays, and then while plotting, I will tell you. So first there is one kind of delay, TCQ. So basically this is pretty direct, clock to Q delay. So it is the delay between clock to Q. But there is another two delays, T setup and T hold. So what it is this is the minimum time. It is a minimum time before the sampling edge. So what is sampling edge now? Sampling edge is something like which stays in the same position without changing the output. So if you see, this is a sampling edge, okay? And that is, it will stay in the same output which was in the earlier state. There is no change in the output. That is sampling state, okay? So now the minimum time before the sampling, before the sampling edge, when the data should be stabilized. Data should be stabilized, okay? Should have been stabilized. So this is called T setup. So if you see, there is this sampling time, right? There is a T hold before this sampling time, which should be done. That is, the data should be stabilized there. It should not go after it. Okay. So that particular delay is T setup. We'll come to more detail like about this later, but now you can learn what it means. Next is T hold. T hold is basically the same minimum time which is required after the sampling edge. So it is after the sampling edge when the data should be stabilized. Should be stable, okay? So here this T hold is easier to show you here. Basically this particular time. This time, this is where the data will be basically like trying to become stable, and at this point it will become stable. So this entire will be T hold, okay? So this entire time will be T hold. And for a sampling edge, anything before this sampling edge will be. So if you see here T hold, it happens after the sampling edge. Till here it was constant after your sampling edge. And any time here before the sampling edge starts, you have to make sure that it is stable. This will be T setup. Okay. And also there was one more thing. So we also call it as transparent and opaque. There are two terms, transparent and opaque. So if you see, transparent is somewhere where the data goes in. Data is go through. Data is let through. And opaque is where data is not let through. That is, older data exists. Data is not through. So at this point, if you see, let's say for master and slave, we are trying to divide into transparent and opaque. Master is a negative latch. So in the negative level, master will be transparent. Your slave is positive latch, so slave will be opaque. Now this is positive. So in positive, the master will be, what will the master be?
Master will be opaque.
Will be opaque and the slave would be transparent.
Correct. And similarly, it proceeds. Again, master is transparent, slave is opaque. So on, it goes on. Okay. So you're transparent somewhere, the data goes through that particular stage, and opaque is where data does not go through and the older value is retained. Okay. Okay. So okay. So now we'll talk about another way of denoting this particular, let's say, circuit itself. That is using tri-state. So you have already seen about tri-state, right? something like this. Right, so you have already seen this tri-state earlier. So here, how you will use tri-state inverter is, so basically what we will do is, same thing, the same D latch. So yeah, so the same D latch. What we will do is, we have a D input, then we give this particular enable signal, we will get Q. So for this, what will be the output that you will get? When the enable is 1, you will get your Y as D bar. Okay. And when your enable is equal to 0, your Y will become high impedance. You will get high impedance. Okay. Floated, basically the output is floated. So this is the main, like, kind of how you will use a tri-state to construct the latch. Now, to write it detailedly or draw it detailedly, let's say you have a D input, then you have a here tri-state inverter, which is the signal given is clock, and then this will be your Q bar, right? Because you will get D bar here, so you will get Q bar here. So this will be given to another inverter here, that will give you Q. So now this Q will again be taken and given as another tri-state inverter here, and here it will be negative triggered. So here a clock bar is given, where again this will go and reach here at this point. So let's name, this will be T0, I'll call this inverter 1, and this will be tri-state 2. So basically it is also the same output, you'll get the same output. At the end of the day, it is also a D latch itself. This is also a D latch, but the only thing is it is in a different structure. So now let's plot for this. Okay, clock, we'll start with the clock. So you should be very sure of how the clock works, like all the clock signals, how the values are going, and how you're able to plot and so on. So we will start with the clock. Then let's say, okay, let's plot the clock bar also. So it will basically be opposite to clock. Okay. So now next we have D. Let's say my input D, I'm giving something like this, then from here I have this. Let's say I'm just leaving it, okay? So if this is my D now. Now, what happens is, now you tell me for T0 and T2, which is opaque and which is transparent from above here. T2 positive, T0 is positive, T2 here is negative. So now T0 at this point will be opaque or transparent.
T0 is opaque and T2.
Okay, let's say this is positive here. Okay, now this is positive. Now let me. Any answer? So what is T0?
T0 is opaque and T2 is transparent.
Correct. T0 is opaque and T2 is transparent. Similarly, here your T0 will be
transparent and T2 is opaque.
Correct. And so on. And it will proceed so on. Okay. So this will be your T2 and T0, T2. And finally, when your D is something like this, what you will get your Q is, so for your D flip flop, initially what will happen? It is a don't care condition, and then you will get whatever is in D. So after some sort of delay, you will get what is in D here, that is this one, right? So you will get this particular thing. Now, if you see at this point, here it should come, right? But after some delay, it will go here. Okay. And then it will go to the negative side. And negative side, what happens? Nothing will happen. It will just remain whatever was there in the previous thing. So that will remain till the next particular uh, what do you call level, positive level. Till then, it will remain the same. And then again, the same thing will happen. D starts here, but it will start from here. There is a small delay. And then whatever is in the positive side, that will happen. And once negative starts, again it will continue till the negative. Okay. So now if you see this delay here, right? This delay here, this particular one should start here, but there is a delay here. This delay will be calculated as T0 and Ti1. T0 plus Ti1. Okay. So basically today we saw basic things like D flip flop, D latch, and how the state diagram and how the state changes happen for D and flip flop and latch, and also how it can be denoted like using multiplexer, using tri-state inverter, and so on. And another important one was master slave D flip flop. And there are two main delays, T setup and T hold. Setup is something that happens before the sampling edge, and hold is something happens after the sampling edge. So after the sampling edge, when you need a certain amount of time, the minimum time for the data to get stable, that is hold. And before the sampling, the time to get stable, that will be T setup. Okay, so you have this, and then I think remaining we have to talk about same thing, tri-state inverter. We'll be using tri-state inverter for master slave flip flop, and we can see how graph works for that. And then I think, yeah, it's pretty much that. Then we'll look into how there is this transfer characteristic graph. So we will see the transfer characteristic for that. And then I think we can solve few practice assignments. So for today, do you have any doubts in whatever we covered today? Okay, if there are no doubts, then